Welcome to a video on stability criteria for homogeneous linear ordinary differential equations. In this video, you will see that it's possible to determine the stability of a homogeneous linear ordinary differential equation just by looking at the coefficients, carefully looking at the coefficients of the characteristic polynomial. First of all, I would like to discuss with you what is stability, and then we will see how we can determine stability and what alternatives exist in order to judge the stability of a linear ordinary differential equation. So usually in mechanics what you get are second order homogeneous linear ordinary differential equations if you are interested in self-excitation. If you have some other kinds of excitation, you will get inhomogeneous linear ordinary differential equation, but they are always of second order. The dynamic systems that are usually considered in mathematics, so for theory, are just first order system. Now you can write every second order system as a first order system by introducing auxiliary variables. So take the velocity, for example, then you would take the first order derivative of the velocity, which would then be the acceleration, and for the acceleration you would have your second order derivative, and then you could take at the same time the displacements, and the first order derivative would be the velocities. So by taking a combined state vector of displacements and velocities, you will arrive at a first order system from the second order system that needs just the first order derivative. Now the question is, what is stability of a solution of such a dynamic system? Well, that definition has been given by Lyapunov. It reads a little bit difficult, so it's written that you start. I would try to start with the end a little bit. You find for every epsilon, you find a delta, such that if you start with initial condition, your trajectory with inside that delta environment, then you end up for the solution always in an epsilon environment, so to speak. So there is one solution x naught, that is the reference solution, and there are some other solutions starting with perturbed initial condition. The perturbation is controlled by that delta parameter here, and all these trajectories remain in an epsilon tube, so to speak, around that reference trajectory x naught. That's what this definition tells you. Yeah. So again, you have I would say a delta ball, or in 2D a circle of radius delta around the initial condition of your reference trajectory, and then you can be sure. Yeah? So for every epsilon there exists such a delta. So for every, if you want to control the whole solution in that epsilon tube, you are sure that there must be a delta if the solution is stable, in which you select your initial condition, and then you know all these trajectories that emerge from these initial conditions, they will be contained in this epsilon tube. So with giving that epsilon and finding the correct delta, you would be able to control the solution and therefore stable. Control the solution in the sense that the perturbation, so the deviation from the reference trajectory, is epsilon small when measured by an appropriated norm, for example by the Euclidean norm. So in short, a sufficiently small perturbation, small with respect to this delta here, always remains small. This is the basic idea of the stability of Lyapunov. For us, the reference solution is the equilibrium solution. So it remains there, and we have our perturbations, these small delta x and delta y. And the question is whether such a situation is given, whether these perturbations always remain small. Yeah? So there are additional definitions that can be used, namely a solution cannot be only stable, it can also be, or a reference trajectory cannot be only stable, it can also be attractive. Attractive means something that you do not have here. You only know that neighboring trajectories will be inside that epsilon tube. For a solution to be attractive, these neighboring trajectories that start at neighboring or emerge from neighboring initial condition, their difference converges to 0 if you consider t to infinity. So this attractivity is an asymptotic result. Stability is a result along the whole trajectory, this tube, while attractiveness is something that refers to the asymptotics. So asymptotically, if you start in a surrounding of that reference trajectory, you will end finally, after infinitely many time, of course, you will end at the reference solution. This is, for example, the case if you consider a pendulum that has damping. So classical damping, of course, nothing special. So then if you wait long enough, well, the solution will end up with, for example, if it's a classical pendulum, in the vertical position. So that vertical position would be attractive. Okay, now we can combine the two effects, because stability refers to the whole trajectory, to the tube. Attractiveness refers to the asymptotic behavior. So let's combine these two. So let's demand a stable reference trajectory that is also attractive. And this would be asymptotic stability then. So the reference trajectory is asymptotic stable if it's stable, so no chance to escape from the epsilon tube, and attractive, so at the very end you will be at x0. A trajectory is called neutral stable if it's stable but not asymptotic stable. This would be the case if you consider a pendulum, for example, without any damping. Then you would, for example, rotate. If you consider a pendulum that overshoots, but also if your pendulum has the classical sway motion, then you would be stable, but you would not reach, for example, the vertical position. You would cross it. You would not deviate, not larger than a certain epsilon from that reference solution, that vertical solution, but you would not converge to it because there's no damping in the system. Okay, theoretical result. But this would be neutral stable. And then there must be the opposite of being stable, and that's unstable. So x0, the trajectory is called unstable if it's not stable. Okay. So how can we determine the stability of a trajectory? Well, the first result is due to Lyapunov, and it can be obtained, for example, by making the classical, we know we have a linear ordinary differential equation, so by making the classical exponential setting, looking at the roots of the characteristic polynomial, and as I explained in the last videos, we look at the real parts of all the roots, and if all the real parts are negative, then we have not only stability, but we do have already asymptotic stability, because due to that exponential decrease, there is a decay of the perturbations to 0. So we converge to the reference solution. So this is the theorem of first part of the theorems of Lyapunov. So if all the real parts of all roots of the characteristic polynomial are negative, so you make this exponential setting, you compute the roots of the characteristic polynomial, you know that these exponential terms then compose the general solution of the ordinary differential equation, and if all the real parts are negative, then these perturbations converge to 0, so we have asymptotic stability. But if there's at least one root with a positive real part, then already we have instability, because that contribution grows and becomes infinitely large. No, then there could be a third part, namely that not all the roots are negative, but there's also no positive real part. There could be a zero real part, an imaginary part. You know that imaginary part, the purely imaginary solution, corresponds to cosine and sine harmonics. You can see it for the undamped free vibrations. So then, in this case, undamped free vibration, asymptotic stability is not possible. So if there is no positive real part, but at least one real part of a root is vanishing, so we are neither in the second case, because there is no positive real part, but we are neither in the first case, where all the roots have to be negative, so there is at least one real part that is vanishing, so there is a complex conjugate root, then asymptotic stability is impossible. So this would be the case for the single degree of freedom oscillator. But these are classical results due to Lyapunov, and you can follow these results, and we followed them in the past in machine dynamics, also in this course here, when we analyzed. So we just made a setting for the homogeneous solution, and then we analyzed the eigenvalues and the real parts of the eigenvalues. In many places, also in vibration theory, this is done. However, the question here is a fundamental different question. Can we already infer from the coefficients of the characteristic polynomial what happens with the sign of the real parts? So can we compute, instead of all the roots of the characteristic polynomials, can we assess stability already from the coefficients a sub I of the characteristic polynomial? That would be much more efficient. And one answer is due to Hurwitz. One has to say Hurwitz gave the answer in the German literature, Root gave the answer in the Anglo-American literature. So it's the famous Root-Hurwitz criterion, independently obtained by Root and Hurwitz. So first of all, you have to somehow normalize your characteristic polynomial in such a way that a sub n, so the coefficient of the highest power, is positive. Then you have that standard form. And then the result is all the roots have negative real parts if all coefficients of the characteristic polynomials are positive. So this is a necessary condition. So you can check after normalization, of course, so getting the correct sign for a sub n, you can check the sign of all the other coefficients of the characteristic polynomial. If you find a negative sign, you can be sure that there must be that you can exclude asymptotic stability. There must be something that some real part that is either zero or positive, because otherwise the coefficients must be positive. No? So if you find set an larger than zero, if you find another coefficient that is negative, you can already exclude asymptotic stability. Yeah? Here. Yeah? So if there is one coefficient less or equal to zero, then asymptotic stability is impossible. But that's good, but that does not help us completely, because it's only a necessary condition. It's not a sufficient condition. So how can we obtain a sufficient coefficient condition? That question was also answered by Hurwitz. You look at the minors of that special matrix. First of all, what kind of matrix is it? It is a so-called Hurwitz matrix. Yeah? How is that Hurwitz matrix be structured? Well, you start, maybe one looks at the first two rows here, you start with a sub n in the second row, with a sub n minus 1 in the first row, and then you write all the coefficients, starting so with the highest coefficients, so a n minus 3, you always skip one, a n minus 5, and so on. And you do this, well, of course, until you have no coefficients left, and then you insert zeros at the matrix, such that the matrix is an n by n matrix. for the next two rows of that n by n matrix, you shift the whole procedure at one position to the right. You do this until the last rows, where you really end up then with A0, A2, and with 0, A sub 1 here in the last columns. And this is an n by n matrix. So this is the matrix Hurwitz invented to study the stability. This was the idea of Root and Hurwitz. Now you need positive principal minors of that matrix. What is a positive principal minor of a matrix? Well, you take the first k columns and the first k rows, so you take a submatrix of that matrix and you determine the determinant. You compute the determinant. So all the determinant of these submatrices that are obtained by starting here, so on the left and on the top, and going down k steps to the right and downwards. And then you obtain a submatrix, and from that submatrix you compute the determinant. And if all these determinants are positive, then you are sure that all the real parts of all the roots are negative. And this is a necessary and sufficient condition. That's a big advantage. Now you might argue that, well, that's a lot of work, right? Just checking the coefficients is much less work than checking the Hurwitz matrix. Can we do things a little bit simpler? And this answer has been given. First of all, there has been a simplification of this result, which is due to Lienhardt and Schippert. They said, well, it's not necessary to check all the minors if we check these coefficients of the characteristic polynomial. Namely, the real parts of our roots are negative is equivalent to having positive values of every second, starting with A0 here, coefficient of the characteristic polynomial. Of course, an is positive, so normalization of the characteristic polynomial in that way with respect to the sign. And you check also every second minor, starting with h sub 1, h sub 3, and so on. And even that appears to be too, well, inefficient in many cases, because in many cases you have a physical dependence. So now physics comes into play. Until there, these are mathematical results and we are done. From physics, you know, there might be a parameter, well, for example, a rotational speed, and you are really, really sure that that rotational speed, if it's 0 or close to 0, very, very small, your system is stable. However, if you increase that parameter, then instability might happen. That's what we saw. We supposed that due to the self-centering effect, where we press in one direction and where the displacement goes in the opposite direction. So we think that it could be that for higher rotational speed, the system becomes unstable. And we have a continuous dependence on that parameter, on the rotational speed. And we are also sure that for low rotational speed, nothing unstable, nothing strange, mysterious should happen. So then, there are two ways that we obtain, that we deviate from asymptotic stability. So there are two mechanisms to lose stability. The first one is related to the first criterion here, but just to one coefficient, namely to the coefficient A0. A0 can become negative. This is the case if one purely real root becomes then positive. So the real part then obviously is positive. It's a real root. No? And this is monotonic instability. Monotonic instability because it's a purely real root. It's not a complex conjugate. It has no imaginary part. The imaginary part would be some kind of oscillation. And for that unstable mechanism, so for this root, there is no complex conjugate. There is no imaginary part. It's purely real. And therefore, this would be some kind of monotonic instability. You would go by exponentially to infinity without any additional harmonic functions, sine or cosine functions, so without any additional rotations. Yeah? And finally, the principal minor hn minus 1 can become negative, and then the real part of a conjugate complex root pair, so it's now the second part here of that criterion, becomes positive, and then we have oscillations and amplitudes that are growing, and this is termed flutter. Yeah? So you have flutter, 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 these harmonic oscillations, and their amplitudes become stronger and stronger, so larger and larger. Yeah? In contrast, for the first one, you just deviate as exponentially to infinity. Yeah? So these two different mechanisms exist, and they are rooted in two different properties, namely they can be found from the coefficient a naught or from the principal minor h sub n minus 1. Now the big question is, what happens here for our system, for our rotor in a journal bearing? Is it a monotonic instability, or is it a flutter instability that the system suffers from if we increase the rotational speed? What do you think? Well, I will tell you the answer, but in the next video. Thank you very much for watching.